Hi students, in this class we are going to solve a numerical problem on the economics of power factor improvement. That is, we will find out how much amount can be saved in the electricity bill if you improve the power factor using a capacitor bank. Even though we have to spend certain amount towards the capacitor bank, still we can save certain amount in the electricity bill. The load is 800 kilowatt. Its initial power factor is 0.8 and we are going to improve the power factor up to 0.9, and this load works for 3000 hours per year. Here the tariff is given. The term tariff means the cost of electricity bill. It is rupees 100 per kVA plus 20 paise per kWh. If you look at the electricity bill at your home, you have to pay the bill according to the kWh usage or according to the number of units you are using in a month. But when it comes to the industrial consumer, he has to pay two parts in the tariff. One is according to the number of units consumed, and the second one is according to the kVA demand. So when you look at the tariff of the industrial consumer, there are two parts. One is according to the units consumed. The second one is according to the kVA demand. The cost of capacitor bank is given as rupees 60 per kVAr. And the annual depreciation of the capacitor bank is 10%. First of all, we will find out the rating of the capacitor bank in order to improve the power factor. Then we will find out the annual cost before power factor correction. Before connecting the capacitor bank, what is his electricity bill? Then we will find out his electricity bill after connecting the capacitor bank. Then we will find out if there is any saving in his electricity bill. This is what we are going to solve. We are going to do in this problem. Let's find out the rating of capacitor bank first. The power rating is given as 800 kilowatt and its initial power factor is cos phi 1 is equal to 0.8, and from this you can easily find out tan phi 1, which is equal to 0.75. We have to improve the power factor up to 0.9. So cos phi 2 is 0.9. We can find out the corresponding tan phi 2. It's equal to 0.4843. Now we will find out the kVAr rating of the capacitor bank. kVAr rating of capacitor bank. So this is equal to the power in kilowatts, because this is in kilo, so this should also be in kilo. Power into, it is tan phi 1 minus tan phi 2. So it is equal to 800 into tan phi 1 is 0.75 minus tan phi 2 is 0.4843. So kVAr rating is equal to 212.56 kVAr. This is the rating of the capacitor bank required in order to improve the power factor. Now we will find out the electricity bill of the consumer before connecting the capacitor bank. As I said earlier, we need to consider two parts here. One is his kVA demand, second is his energy consumption, his kWh consumption. Because this industrial consumer has to pay the electricity bill according to both kVA demand and kWh usage. Now his maximum kVA demand is equal to kW divided by cos phi, because W is equal to VI cos phi. Watts is equal to volt amperes into cos phi, or kilowatts is equal to kilovolt amperes into cos phi. So kVA is equal to kW divided by cos phi. This is equal to, the rating of the load is 800 kW divided by power factor is 0.8, that is kVA demand is 1000. Now we'll find out the kVA demand charge. If you look at the question, the tariff is rupees 100 per kVA. That is 100 into, what is the kVA? It is 1000 kVA. So total charge is equal to rupees 1 lakh. This is the kVA demand charge. Now we have to find out the kWh charge. So first we'll find out the units consumed per year. The load is 800 kilowatt. What is the units consumed? It is kWh. Units is kWh. So this is equal to, what is the kW rating? 800 into hours is 3000. You look at the question. We are using the load for 3000 hours per year. That is 800 into 3000, which is equal to 24 lakh. This is this energy consumption in a year. So energy charges is energy charge per year equal to, look at the tariff, it is 20 pice per kWh usage. 20 pice per kWh usage. So 20 pice or 0.2 rupees into kWh usage is 24 lakh. So energy charges is equal to 4 lakh 80,000 rupees. So what is the total amount? Total annual cost is equal to, the kVA demand charges 1 lakh plus the cost towards energy consumption or kWh usage is 4 lakh 80,000 is equal to 1 lakh plus 4 lakh 80,000. So this is equal to 5 lakh 80,000. So this is a spending before power factor correction. Now we will find out what is the cost of his electricity bill after the power factor correction. So here we need to consider the cost of capacitor bank also. What is his kVA demand now? Maximum kVA demand is equal to kW divided by cos phi. Now the power factor is improved. By connecting the capacitor bank, the power factor is improved up to 0.9. So here the cos phi is equal to, 0.9. So this is equal to 888.89. I will find out the kVA demand charge. It is rupees 100 per kVA into the kVA demand is 888.89. So this is equal to 88,889 rupees. This is the kVA demand charge. The energy charges is equal to it is same as before, 4,80,000 rupees. There is no change in the energy charge. It is 4,80,000. Now we have to find out the cost of capacitor bank. Capital cost of capacitor bank. Look at the question. The cost of capacitor bank is rupees 60 per kVAr. What is our kVA rating? It is 212.56. The cost of capacitor bank is equal to rupees 60 into, what is the kVAr rating? 212.56. 60 rupees per kVAr into kVAr rating. This is the cost of capacitor bank. It is equal to 12,753 rupees. But actually we need not to spend this much of amount in a year. The depreciation is given. What is the depreciation of capacitor? Depreciation and interest is equal to 10%. It is just like suppose you buy a car for 10 lakh rupees. After 1 year's usage, you are selling it for 8 lakh rupees. What is the actual spending in 1 year usage? It is only 2 lakh. Because when you sell the car, you are getting the 8 lakh rupees back. Actually, you are spending only 2 lakh rupees. Just like that, the depreciation of the capacitor is only 10%. If you sell the capacitor, the remaining 90% you will get back. So the actual spending is only 10%, which is equal to 0.1 into 12,753, which is equal to 1,275 rupees. This is the spending towards the capacitor bank. So what is the total annual cost after connecting the capacitor bank? kVA demand charge is 88,889. 88,889 plus energy charges 4,80,000 plus the amount towards the capacitor bank is 1,275. So total annual cost is 5,70,164. So this is a spending or is the electricity bill after connecting the capacitor bank. This is the spending before connecting the capacitor bank, 5,80,000 rupees. This is 5,70,000 and something. Now we will find out the savings. So savings is equal to the amount spent before perfect correction minus the amount spent after correction. Amount spent after perfect correction. So this is equal to, what is the amount before correction? 5,80,000. 80,000 minus, what is the amount spent after correction, after connecting the capacitor bank? 5,70,164. 5,70,164. So there is a saving of 9,836 rupees. Even though we spend certain amount towards the capacitor bank, we have this much of savings.